I have these 5 sections of this talk. I understand there's an audience that's very diverse, some people of the general public and a lot of members of this community, so I hope that everyone can get something out of it. I'll start with a pretty basic introduction and then go a little bit into the past of this field, then talk a little bit about from a history or sociology of science perspective, how do fields actually emerge and what do we know about this and where can we then locate ourselves in this process that leads us to arrive in the present and also allows us to take an outlook into the future. And then I'll end with a couple of comments on some structural issues in the organization of science that I think have affected us as a field, but that I think we can also contribute to remedying eventually. So, what is nuclear fusion? I wonder whether we can dim the light a little bit more to increase the contrast of the slides. Yeah, thank you. So, starting with the basics here, I'll focus on the DD reaction, which is the reaction that's most discussed in our field. 2 deuterons. Professor Metzler already talked about this reaction. 2 deuterons come together and they form 1 out of 3 products, either helium-3 and a neutron, or a triton and a proton, or a helium-4, and there is this branching ratio of 50%, and then a small fraction for the later branch, and we can keep that branching ratio in mind because later we'll come across research of Professor Chesky's group that has demonstrated that this branching ratio might not be written in stone. Of course, there is this enormous density that comes from the release of nuclear binding energy, that mass difference that results from fusing nuclei together, which then gets converted into energy. So here we see the E equals mc squared, that relationship from a letter from Einstein. So what's the challenge then? Well, if we bring nuclei together that are positively charged, we have this kind of repulsion, and it's well known that in the sun this is overcome through a combination of density, increased density through gravity, and also kinetic energy of these ions, which we perceive as temperature, and so here you see sort of temperature distribution of the sun. So the sun has been this kind of model of how we think about nuclear fusion for the longest time, and I'm sure you've seen it all in the press when there's now a lot of these fusion startups. The story is usually they try to create a sun on Earth, and so the first tokamak reactor, the most common approach to this, was created in the 1950s, and in the tokamak you have these nuclei that are then racing around, and so you have certain temperature constraints, otherwise the whole thing melts away. And so, and then you have the reaction probability, which is usually treated as given at a specific kinetic energy. And so what you have as a lever is to increase the density, so as to increase the fusion rate. And so that then connects the field of nuclear fusion traditionally very closely with the physics subfield of plasma physics. And just for those less familiar with physics, so some of the work that plasma physicists do is to model the way particles move inside a plasma, the kind of dynamics, this like hydrodynamics-like turbulences that can be modeled and that can be attempted to be controlled. And so that's this kind of marriage between the field of nuclear fusion and the field of plasma physics. And here is a table, not sure how well it can be seen, but that's like, these are the 9 categories of the 9 subfields of physics according to the American Physical Society. And I highlighted here the one that includes plasma physics. And so again, that is the subfield of physics that's been most closely associated with fusion. Now, people from the early days on have thought about whether a metal lattice could be helpful in bringing together nuclei and catalyzing nuclear fusion. And so here you see an early paper from 1926 in Naturwissenschaften, which was later published in English in Nature as well, where the idea of using a palladium lattice was already articulated by the chemist Fritz Panet, who's based in Berlin, I think. So how does the situation look differently when we have a lattice? We have then the metal lattice host atoms or nuclei, and then in between we can have lighter nuclei that we then seek to bring together and have fuse. And so the temperature is much more constrained, of course, in this case, because otherwise our host metal lattice would melt away. The density is higher than in the plasma, but it's also constrained. And so the only lever in this approximation for the fusion rate equation is then to change the reaction probability. And that is where our efforts from a theoretical point of view have all been focused on. And so if we then think about the areas of physics that become relevant here, there's condensed matter physics that looks at the way lattices form and the way lattices change with boundary conditions such as temperature and pressure. Then one can introduce dynamics and think about how smaller nuclei or smaller atoms diffuse in a lattice, like what's been done in this paper, including also the diffusion of defects. There is more global dynamics, like here there's a visualization of an actual femtosecond electron microscope video of phonons in a germanium crystal. Here's a simulation of how that could be visualized in a cartoon. There's also collective quantum effects. So far we've visualized the atoms only as little balls, but really they should be thought of much more complex, more like liquid-like or more abstract type of objects. There's a nice group at the MIT Math department that does these hydrodynamic analogs of quantum effects. So this is a demonstration of superradiance through a hydrodynamic analog where a field interacts with two-level systems. And then so far we've considered atoms, but then we also need to look at the center of atoms. And so at the center of atoms is the nucleus, and the nucleus itself has these kind of dynamics. I showed here this nuclear density functional theory generated video, which kind of shows the nucleus kind of wobbling around. So if we want to think about nuclear fusion in a lattice, there's a whole set of different physics subfields that become relevant here. I've highlighted here nuclear physics, atomic and molecular physics, condensed matter physics, quantum optics. So maybe no wonder there has been such a chasm between the traditional approaches to nuclear fusion that was so closely tied to plasma physics and what we were doing. There's a nice paper in 2019 of scientometric paper that analyzed how much physicists stray from their original fields. And this paper found that here the area of the first year of a researcher marks the rest of her career in the physics publications that they've analyzed over several decades. They also looked at, so this matrix shows these different fields on the y-axis at the beginning of people's career and where they were publishing in, and at the end of their career at the bottom. And even actually from researchers who started publishing in the 80s, there is some sort of migration at times, even though you see the diagonal is where most people stay in their own field. But then actually if we go into the 90s and the 2000s, it becomes even more concentrated on the diagonals. That means that people move even less across these subfields of physics. And that there's especially very little interaction and migration between nuclear physics on the one hand and condensed matter physics. Okay, so I wanted to present this backdrop to help you maybe appreciate a little bit more why the results that I'm going to go over quickly why they had trouble being received, let's put it this way. So solid-state fusion in the past, I'm going to show you a bunch of iconic experiments. Of course, this is just going to be a selection. It can't be comprehensive in this format, but I just want to emphasize here that there have been a large variety of different experimental configurations, electrolysis, gas-loaded experiments, low-energy ion beam bombardments, like what Konrad's group has specialized in. And then there's also a large variety of characterization modes. People look at heat or energetic particles, new element formation. But at the level of the lattice, we can think of these as very similar systems. Even macroscopically, they're generated differently, and there are different diagnostics put to work. So here, maybe the most iconic experiments is the 1989 Fleischmann-Pons experiments, here reported in 1990 in more detail, where there was this palladium foil that's been electrochemically charged with deuterium, and the researchers reported this big increase in temperature, which over a longer period of time corresponded to about 20 megajoules of energy, which is about more than 100 times what would have been expected from the chemical reaction of the deuterium in that system. So that was the sort of initial trigger. A similar experiment was later shown to, or suggested to have produced helium-4, which is here shown in commensurate amounts to the amount of excess heat that was measured. There is also similar experiments where neutron detectors went off next to the detectors, showed these kind of bursts you see on the right compared to background ones here shown on the left. There were similar experiments where solid-state track detectors were used with characteristic tracks of neutron-induced reactions that look very similar to neutron-induced tracks from a known source. And then there is the ion beam work, where Konrad Czesky's group is I think it's fair to say, the leading group in the world in this area, that have shown that if you come actually down from deuteron energy levels in the realm of traditional nuclear fusion research, and you come down, the reaction rates are actually higher than what you would conventionally expect. So this reaction probability is indeed not as simple as people might have assumed, and it's a complex thing, and it's affected by the surrounding environment. Here is also work from Konrad's group on the right. It's hard to see here. I'm just going to tell you what it is. It's a change in branching ratio as a function of, or as a function of energy at the low energy regime as dependent on the environment. And then there are experiments that show various morphological features like craters on the surface, and also elemental analysis suggests that there is a transmutation, there's formation of low Z elements, for instance, in this experiment. So people have put forth various criticisms of these experiments, and that has been sometimes fair and sometimes not so fair. But I think one can say it's a fact that there's a large body of experimental reports, and taken together, this body of experimental reports strongly suggests the presence of anomalies. And still there is continued controversy. There's of course a lack of funding, a lack of coverage, a lack of publicity, which might be appropriate. Which, if the claims here are true, then one would expect a lot more, let's put it this way, funding and attention, especially if you look now at the thermonuclear fusion industry. And so I think that will have to lead us to state that there isn't, this hasn't really fully formed as a field, or this hasn't fully emerged as a field. Otherwise, there wouldn't be this controversy. And so I'm saying here there's been not enough convergence around a reference experiment and also an actionable explanation as to what's going on. And so that motivates here this little intermezzo where I ask, okay, how do fields emerge? What do we know about this, and what might we learn about this, or how can we locate our own fields' evolution in that regard? And so I'm going to quickly talk about some research I did, some history of science research on the history of the transistor, which is of course the basis for the computer chip. And it's typically the invention of the transistor, or the emergence of the semiconductor field, is typically associated with the date 1947-48, when there was actually 48 was the physical review letter by the three inventors, three scientists at Bell Labs that were later described as the inventors and received Nobel Prizes. So they're seen here. There's also this narrative around this invention period as being the magic months, where people, these geniuses in what was sometimes called the House of Magic, Bell Labs, so came up with this brilliant idea. But then actually, if one looks a little bit deeper, there were actually anomaly reports of amplification, unexpected amplification in solid state material, solid state crystals already as early as the late 1910s. And so these reports have been published, but their mechanism was unknown. There were transistor patents as early as 1925, or they were not called transistors, but solid state amplifiers. And so this led some science commentators, like the editor of Radio News, Hugo Gernsback, in 1925, to state the semiconductor crystal now replaces the vacuum tube. This is a revolutionary invention. And this explains how some radio experimenters have been able to obtain such remarkable long-distance records by unexpected amplification. And then even several years later, you had other commentators here, the famous physicist Wolfgang Pauli, say, no, one shouldn't work on semiconductors. He discourages students to work on this. It's such a mess. Who knows whether semiconductors even exist? And so you see maybe parallels to this field. There is this controversy, this ambiguity, this lack of clarity, whether there are anomalies, what is the potential, whether there are potential explanations, or whether something's actionable. And so this period, this pre-period, this is, let me see if I can point here. No, I'm just going to describe this. So this pre-period before 1948 was also marked by, there were several thousand publications in total on these semiconductor crystals. And so there was a whole lot of activity, but you can also see in this graph at the top, which are the publications over the years, that this really took off in 1948, and so that's kind of marks an inflection point where the field has really fully formed and overcome this ambiguous period. And so, yeah, so this was marked by this 1948 physical review letter, and afterwards then you had a follow-on innovation and moving towards the MOSFET transistor. So if we look at this pre-period more, there's basically insights that have been gained about anomalies. So I've listed here a bunch of different key insights about people having learned more and more to produce anomalies reliably and in different materials at different settings. People learned about these kind of materials, for instance, how to grow single crystals and the importance of single crystals, the relevance of elemental semiconductors like germanium and silicon, and then also the commensurate development of theory and sort of band structure theory derived from solid state physics. And so you had all these developments, and then you had eventually this integration effort by Bell Labs. So Bell Labs and these folks in the solid state physics group, they were not the people that invented the transistor out of nothing, but they were basically very good at tapping into these various communities and following this cumulative this buildup of knowledge and then integrating it and making it actionable. And so what you had with this 1948 physical review letter was, for the first time, reasonable understanding of what's happening and also reasonable reliability in generating the effect. And that caused that kind of phase change in the field and that expansion of activity. And so I think there are some parallels, and so I've tried to make a similar timeline for our field, where over the years, especially since 1989, different designs or different experiments have emerged, or different modalities of experiments, and also different kind of knowledge has been gained, both when it comes to, in this case, producing anomalies or producing anomalous observations, and in different configurations, but also in a better understanding metal hydrides, how to have more control over producing certain materials, both by this community and also by other researchers working or interested in metal hydrides for other reasons. And then also the development of theory and the integration of knowledge across these different physics subfields. And so, I think maybe what also similar, maybe Conrad means something similar when he says, I think we're close. I also think we're close. I think there is maybe the opportunity now for a similar type of integration of knowledge that has been gained and has been accumulated in a maybe initially in a less coordinated way, but that can now be brought together. And in right now and in recent years, we've seen activity from quite eminent organizations and groups in this space. I mean, these are all organizations that have been involved in solid-state fusion or cold fusion research, if you like. And also, there was a very nice top-tier journal, peer-reviewed article by Conrad recently, but there's a really nice experimental work and the dissertation of Eric Ziem at the University of Illinois, for instance. There's a solid-state fusion website that starts to collect and aggregate knowledge and have a different sort of public face to this all. So there's interesting and exciting developments. And so we could maybe speculate a bit and say what could come out of this. One possible scenario I'm painting here is to say, well, I think it's quite likely that there will be one or several high-level experimental publications in the coming years that deal with the kind of criticism that has been articulated, that there needs to be more detailed diagnostics, there need to be more detailed characterization of samples, higher reproducibility, better controls, longer runs, these kind of things. I think it's also likely that there'll be further convergence of knowledge across condensed matter physics, nuclear physics, and quantum optics. I think it's really fascinating to see your theory development, Conrad, but also the work I'm most familiar with of Peter Hagelstein at MIT, and also the sort of touch points between those, but then also the touch points with other communities, like the quantum batteries community, the accelerated exciton diffusion community that looks at organic solar cells, and the nuclear quantum dynamics community. So I think there's exciting opportunities there. And if that is indeed the case, then for sure resources will flow into this area, new research programs will open up, and research on solid-state fusion will become institutionalized. And that, I think, is when systematic technology development commences. I think this is when you have a TRL level. I think right now we don't have a TRL level. We're in this pre-period where we're working towards that. Okay, so I thought a little bit, okay, what might we be able to expect from solid-state fusion technology? And here, I think this is really just a bit of back of the envelope thinking, but I think it could be interesting and fun and useful to engage in this from time to time. If we look at the Japanese nanoparticle results, where there is a large temperature difference from these gas-loaded nanoparticles, and that if we read those reports, it seems to be quite stable and reliable, and we can quantify that. So let me focus on this here. I mean, if we look at their reports, for instance, 90 watts over a period of 25 days, that's about 53 kilowatt hours, 190 megajoules, that's about 10 keV per deuteron. So that's far beyond the chemical limit. And if in this kind of sample, if we assume a DD reaction to take place, then that's about 1 out of every 2,000 deuterons per taking. So if we now assume that with greater understanding of these systems and theoretical mechanisms that inform modeling, then we could sort of dream up and think about what could be maybe an upper limit in terms of the efficiency. So I'm painting a picture of, say, a 25 by 25 millimeter thin film of 100 nanometer palladium with 10% vacancies, and if we assume these vacancies are filled with deuterons, and 1 out of every 10 vacancy sites has a DD reaction that's then induced, in this case, by a 3 milliwatt laser, similar to the Masco-Matteo or Biberian experiments, then we can sort of put a ballpark number on this if we have several of these layers stacked in a system of, say, in this case, 8 kilowatt hour total capacity of a small cube, basically, of less than a cubic inch. And one could articulate a cost target, and one could talk about how much fuel and helium waste this would produce. But I think, this is all kind of dreaming and envisioning things, but it could be helpful as long as we qualify that, this is not where we're at, but this is what kind of we're striving for. Okay, and I think ultimately what these systems are, they're systems with complex physics but simple engineering compared to thermonuclear fusion approaches, which in many ways have simple physics. At least the nuclear physics is very simple, not necessarily the plasma physics, but if we count that to engineering, then it's very complex engineering. And so this has the potential, this approach, to have these integrated, disposable systems that are maybe one can almost say inspired by nature, because that's how nature works, right? You have these in the leaf, for instance, very complicated, very complex physics, but quite simple engineering, simple materials. Okay, so let me move to the last part here. Structural issues in the organization of science that I think have affected us, and that as we are now talking about getting closer to an inflection point and becoming part of mainstream science, that maybe the things that have affected us and have slowed this field down might also be things that we can point out and help to avoid for other developments in science that have been slowed down similarly. So I've already pointed out, so I'm just going to list a bunch of points here. This one here is discovery it should be seen as a social process rather than this flash of genius picture that Bell Labs has so actively cultivated through their IP department and their PR department, that have focused always the geniuses and not the kind of long social process that has contributed this cumulative knowledge that was later integrated. There is also another thing here, is that science today is not working as well as many think it is. There was a nice paper in Nature earlier this year, also a scientometric paper, where this group of researchers kind of quantified the disruptiveness of different papers and patents, and they find that across different fields, the disruptiveness has been going down over the last decades. And so you would think we have more researchers working in science globally today than ever before, but the overall disruptiveness of developments is going down. This is maybe less surprising if we take a lesson from Thomas Kuhn, the philosopher of science. Here in this essay, The Essential Tension, he wrote such things as: the education in the natural sciences remains a dogmatic initiation in a pre-established tradition that the student is not equipped to evaluate. The single most striking feature of science education is that, to an extent totally unknown in other creative fields, it is conducted entirely through textbooks. and the practitioner of a mature science does not pause to examine divergent modes of explanation or experimentation. There's a movement today of people coming from the sciences, some people also coming from the venture capital world that are frustrated by this stagnation in science, and that have started to think about how scientific institutions can and should be changed and improved. So in this essay by Michael Nielsen and Kanchun Ju, the authors state, science is badly bottlenecked on field formation. In particular, we believe current social processes in science are designed to support work in existing fields, but strongly inhibit work critical to the creation of new fields. So think again about these buckets, the stovepiping, these silos in physics that the earlier scientometric paper pointed out. These authors also state that understanding early signals that a new field is steering and designing to detect and support those signals, that's what new programs should do, and we believe many such signals are actively selected against in existing funding programs, and selecting for them would unlock tremendous latent potential for discovery work. So this kind of thinking, if it propagates, would have certainly helped this field, I think. There's also rampant problem of many scientists, I think, having a poor understanding of reproducibility. There are some good articles about this article in Catalysis about reproducibility and its challenges, but I mean, everyone knows it in a sense intuitively from, Rob Christian has pointed out this example of making a souffle, and the souffle, you follow all the steps in the cookbook, but it's just not working out. Yeah. And so that is the issue of tacit knowledge and omitted or hidden variables. Michael Polanyi, chemist, has written about this very prominently. That seems to be poorly understood. We see this with other examples as well. There is a problem, I think, scientists have with, a lot of scientists with ambiguity. Here are two papers by philosophers that build on Husserl and Heidegger, talking about ambiguity, also connected to neuroscience and the so-called Bayesian brain hypothesis. So if you have a pattern like these points here, and you add additional data points, you may interpret these points as different kind of patterns. You add more points, and then some people, more than others, tempted to make a judgment call and say this is a cat or this is a rooster. But sometimes it's maybe not appropriate to make that judgment call, and sometimes I think we should tolerate ambiguity as scientists for months and for years and maybe for decades. And I think in the formation of this field, or in the case of this field, certainly the need of some certain physicists to make a judgment call early, much earlier than maybe that certainly was warranted, has caused much damage. There's an interesting paper by psychologists about the role of cynicism. So here from the abstract, these 4 studies show that people tend to believe in cynical individuals' cognitive superiority. So, but then actual follow-up research shows that cynical versus less cynical individuals generally do worse on cognitive ability and academic competency tasks, but cynicism is often used as a defense mechanism to cover up insecurities. There is a very interesting paper by a friend of mine, Harald Atmansbacher, who's a retired professor at ETH, Scientific Research Between Orthodoxy and Anomaly, where he distinguishes between 2 different types of anomalies. I've kind of tried to visualize, well, you can barely see it. There's anomalies that are close to the frontier of established knowledge and anomalies that are farther out. So that's, I think, an important distinction. And Harald basically says, if you deal with anomalies that are too far from the frontier of knowledge, then they become not actionable. And so I think we were in this kind of situation. I think that explains some of the inaction around this field, the apathy. But I think, again, when you think about this kind of cumulative knowledge that has been gained over the last decades, I think the knowledge frontier has moved closer to the kind of anomalies that have been reported, and I think that makes it more actionable. So, and then finally, there's this really interesting paper by a psychology professor. The title is "Why Are Modern Scientists So Dull?" And how science selects for perseverance and sociability at the expense of intelligence and creativity. So here I just read some excerpts. Industrious and socially adept individuals better suit. The argument is that the current incentives and advancement mechanisms, they select for industrious and socially adept individuals, which are better suited to incremental science rather than revolutionary science. And the argument here is that creativity is probably associated with independence from group norms, impulsivity, and sensation-seeking, with a style of cognition that involves fluent, associative, and rapid production of many ideas. That reminds me very much of these conferences. And maybe the one or the other of you may find themselves described here in the sentence, elite revolutionary science should therefore be a place that welcomes brilliant, impulsive, inspired, and antisocial oddballs, so long as they are also dedicated truth seekers. Okay, so I think that suggests that also this is the small literature of the personality psychology literature that deals with the personality psychology of scientists. And I think this suggests that we should think about different groups of scientists. There's some scientists who are more builders, who like to do normal science, in the words of Thomas Kuhn, and sort of explore within the frontier of established knowledge. And then there are more the scouts. And of course, I think our community here is full of scouts. And I think what is needed is to kind of connect the scouts and the builders, and that is done by integrators. And I think the ARPA-E program is aiming to do that. There's been a lot of criticism now of the existing institutions of science, but I think also as outsiders or as scouts, one needs to keep in mind that there's also responsibilities, namely making information readily digestible is a form of empathy. Something that metaphysics likes to emphasize, consider to teach. Convincing others is different from gaining understanding for oneself, and both are important. Excluding alternative explanations require careful and often tedious work, so someone has to do that as well before moving on to the next shiny thing. And also avoiding narcissism. So we talked about cynicism among certain people, which is damaging, but narcissism can also be damaging, and I mean here both overt narcissism, which is associated with grandiosity, and also covert narcissism, which is associated with victimization. Okay, so this is an area I'm exploring more with some of my colleagues. I should have said earlier, I'm a nuclear engineer, but I'm also an innovation researcher at MIT at the Industrial Performance Center. And so this is a little bit of a glimpse into what we're doing there. So this would suggest that science and innovation policy can bring together mixed teams of scouts and builders and integrators, create protected spaces where new ideas can be tested without being smothered by incumbent scientists. I think that's also what the ARPA-E program is doing. Encourage a balance between exploration and exploitation, between understanding and convincing, and also provide greater awareness of history, philosophy, and methodology in the education of scientists. Okay, so with that, I want to conclude. So I've covered quite a bunch of topics. I hope that some of you in the field have gotten something out of it, and some of you from the general public have learned something. I just want to say, what a ride we have all been on. I mean, with this field and with this, both the dynamics in terms of the science and also the dynamics in terms of the social processes involved here, and also of course, with the potential impact that we're seeking. So I agree with Konrad. I think we might be able to witness in the near future an inflection point in this field, in the formation of this field, or in the completion of the initial formation of this field. There is potential for a new technology that, as in the words of ARPA-E, may be an ideal form of nuclear energy, and as such would change the world in myriad ways. And this community has been affected by dysfunctions in the science ecosystem. But I think And I think that's important to acknowledge and point out as this field progresses. And I know many of you have already recognized this and also intend to continue to document this and to talk about this, so we can avoid these kind of things continuing. And so I think this is also, our field may also be an interesting case, maybe a central case that can contribute to not just changing the energy space, but also changing the way science is done and organized and thought about. Thank you.